Hi guys, I'm glad to see you, and I'm very glad to be here today on CPP Russia. And I'm glad to introduce you, Phil Nash, author of Catch 2. You know, it's a test framework, and he's a former developer advocate for C++ C++ tools at JetBrains. Sorry. Hi Phil, how are you?
I'm good, thank you. Yes, yeah. So I used to be at JetBrains, just to be clear. Now I'm at SonarSource, still a developer advocate.
Okay. And today, Phil will talk about code lifecycle. It's a very important topic, and it's very important topic for all of us, for developers. I mean, all of us in different roles. In a role when we is a developer and we is a tester or something else like me, like manager. It's very important. I want to hear new things for me, new topics for me from your talk. And so, Phil, be ready.
Yeah, I think we should just get into it. I've got lots of material, so let's not hang about.
Let's start.
Okay.
Let's start.
There we go. So that's my title slide. Now, if the title itself wasn't familiar, maybe the title slide looks more familiar. I don't know how well known the book Zen and the Art of Motorcycle Maintenance is in Russia, but that's clearly where this is coming from. That will come up a little bit later in the talk. But yeah, so as you've heard, I'm Phil Nash, developer advocate at SonarSource. So you've got my Twitter handle there as well. Now, what is this talk really about? So we mentioned code lifecycle maintenance. Really, it's about something slightly different to that. Before I get to that, I want to tell you where it came from. So if you know me, you know I do lots of talks, too many probably. In fact, I keep track of them on my website, and I was counting them up just recently. And since 2015, apparently I've done 116 talks. That's way too many. In fact, every time I give a version of this talk, I've now got to update that number. So maybe I won't do that in the future. So why am I telling you this? Well, as I was looking at this, I realized most of them actually just broke down into 4 general categories. Testing, of course, I'm well known for testing. Functional programming techniques, done a few talks in that area. Error handling, there's 2 main talks that I've done a few times, including at C++ Russia, I believe. And 1 talk on simplicity, just the 1 talk, but actually I've reused material from that in most of my other talks, so that's quite an important one as well. So 4 broad categories cover most of my talks, but even then, if you pick at that thread, I realized there was still a common thread to all of those, and that's software quality. Really, all of those are aspects of software quality. And that's what this talk's going to be about. Take a bit of a step back and look at software quality in general. In fact, we're going to go a little bit further than that, as we'll see. But before we get to that, I think we really need to define what software quality actually is, because we may all have different ideas about that. In fact, that's a bit of a problem. Now, there's a blog that I often follow, The Shape of Code, Derek Jones, who's the author of a book on evidence-based software engineering. So it's always coming up with very interesting statistics. But this post from earlier this year, back in March, I think, The Aura of Software Quality, it tells us what he thinks about this. And there's quite an amusing quote here where he says that people in industry are very interested in software quality, and sometimes they have the confusing experience of talking to me about it. A little bit further down in the same paragraph, it gets right to the point. Software quality is a meaningless marketing term. Okay, so what's the problem with software quality? It's a good thing, isn't it? Well, it's not that he's against software quality. He's against people actually talking about it using that name, because it means something different to every person. And if you're having a conversation, you're talking about different things, that's not going to be very productive. So he writes it off as a meaningless marketing term. And of course, we have this cartoon. I'm sure we're all familiar with it. The only valid measurement of code quality, WTS per minute. And we enjoy this cartoon because we can relate to it. There's this idea that quality is something that you know it when you see it, but it can be quite hard to define it for various reasons, including the ones that Derek Jones got to. And that leads us back to the book that the title's based on. So this is the actual book cover, Zen and the Art of Motorcycle Maintenance by Robert Pirsig. If you're not familiar with the book, or at least you've never read it, I do encourage you to do so. It's very interesting. Subtitle, An Inquiry into Values. What's interesting, though, is it's really about the metaphysics of quality, set within a narrative of a road trip across the US. And a big part of that is talking about quality. And in particular, that you can't define it. Sounds familiar? So what the author actually ends up doing, after proving that it's undefinable, is then trying to split it or divide it into what he calls classical and romantic quality. That's sort of the classical quality is the how things work, the engineering side of it. And then the romantic quality is the how things look or how they're used. So slightly different aspects. And to begin with, it sounds like he's very much on the engineering side, hence the motorcycle maintenance. But actually, the conclusion is you need both sides, and they need to work together. Interestingly, a less well-known book is the follow-up, Lila, where he continues the discussion of the metaphysics of quality, but there he divides it into static and dynamic quality. So they're terms that we're familiar with in software development circles. It means something slightly different here. So static quality is or rather dynamic quality is sort of the in the moment as something is happening, like the leading edge of reality, he calls it, whereas static quality is what's left behind in the wake. So like the first time you hear a song, for example, a new song, that's dynamic quality. Now, if you listen to the same song 100 times, you might still appreciate the quality of it, but it's a different quality now. That's the static quality. So really interesting way of dividing up the world. But the underlying fault there is it's really hard to define what quality is. So Wikipedia has a go. There's a page on software quality there. I've pulled out a few quotes from it. It's not all of them, so do read that yourself. Most of the quotes there, I'm not going to read them all, but most of them relate to how your software actually applies to the job it's intended for, how it meets the requirements, if you like. And I particularly like Jerry Weinberg's quote there near the end. Quality is value to some person. So like suitably vague. As long as it's providing value, then it must have some quality. And according to Weinberg, that's the most important aspect. So a number of attempts to define software quality going off in different directions. What would be really nice if there was some sort of standard for what software quality actually means. And there is. There's the CISQ, the Consortium for Information and Software Quality. Sounds promising. And that actually, well, it divides, again, quality up into a number of different things. Primarily structural quality is what we're most used to thinking about. So structural quality refers to the software's security, reliability, performance efficiency, and maintainability. Right, there's a list that we can actually get our heads around. Let's put that into a list form. So 4 sub-qualities, if you like. Now, before I came across this, I was actually working on my own list. And if you stack that up against the CISQ list, it actually corresponds reasonably well. Maybe the biggest divergence is in the first pairing. So yeah, security and correctness are not the same thing. There's clearly an overlap. I'm not a security expert, so I'm going to stick to just the correctness side of it, which will get you a long way there anyway. Reliability, we seem to be matched up on. Interestingly, they put performance efficiency. Mine is performance/efficiency, like slightly different aspects of more or less the same thing. And then for maintainability, I've got malleability or evolvability and how easy things are to change over time. Maintainability, that's a pretty good match, I think, but I'm more focused on how you achieve that. Then I'd add one more to that core list, and that's what I call reasonability, which is obviously closely related to maintainability, but I think it's worthy of a separate category. I will also add in the bit that the Wikipedia page was really talking about, what I call applicability, which CISQ actually does talk about in a separate section. It's just not part of the structural qualities. So now we've got 6 sub-qualities. I'm going to stick with my list for now. Now, when you have a list of things, it's often tempting to take the initial letters and see if you can make an acronym for them. And I'm no stranger to this. So I had to go with these letters. Unfortunately, the best I could come up with was Mr. Crap, and it didn't seem particularly appealing. So I had another look, and Where I've got those two pairings that have alternate words, performance, efficiency, malleability, evolvability. If we go with the second words, the ones that begin with E, oh, I missed a stage here, then we actually have some more promising letters. We shuffle those around. We can actually get career out of that. Who thought you can make a career out of software quality? Not really consider myself a career programmer. Maybe it's not too late to start. Can be useful to come up with an acronym just to keep you focused and to remember that there's these things that we're working on. But more importantly are the 6 subqualities themselves: correctness, applicability, reliability, evolvability, efficiency, and reasonability. At least they're my terms. So far, so good. These all sound like things worth pursuing. Great. That's not what this talk's about, at least not directly. So what I found is, in a lot of the talks that I've given before, I'm actually more interested in the intersection between some of these things, where they overlap, where the trade-offs are, where the friction is, or where things work together to actually produce something even greater than the whole. That's what interests me the most, and that's what this talk's about. So we've got these little bubbles there. We can actually start picking some of these pairings off and investigate those overlaps. So the first one we're going to look at is the intersection between applicability and correctness. Now we might phrase this as doing the right thing, applicability, versus doing the thing right, that's correctness. And if that sounds familiar, there's a maxim that we can trace back to Russell Ackoff, systems theorist. He's often quoted as saying, it's better to do the right thing wrong than the wrong thing right. And there's actually a longer quote that comes from. The righter we do the wrong thing, the wronger we become. When we make a mistake doing the wrong thing and correct it, we become wronger. And when we make a mistake doing the right thing and correct it, we become righter. Therefore, original quote, it's better to do the right thing wrong than the wrong thing right. And that sounds reasonable. It's a sort of gospel in business circles, so that's why it's familiar. But people don't usually look just beyond that quote, because the next paragraph actually says, this is very significant because almost every problem confronting our society is a result of the fact that our public policymakers are doing the wrong things and are trying to do them righter. So Ackoff was a systems theorist, and he wasn't really talking about software development as such. In fact, he was specifically thinking about society and policymakers. So does this even apply to software development? Are there different rules? Well, we sort of adopted this quote coming from the business side of things and taken it as read. But Adam Kelly is someone who's challenged that. He's done a talk, do it right and then do the right thing. He suggests that's the better order to do it in. And to back this up, he presents this chart that's based on a study. Watch his talk for full details. So you've got these 4 quadrants, which are all to do with businesses that have an IT department, which usually involves software development, and broken it down into IT spending and sales and growth. Put some figures to it, and then puts them into this chart. And clearly, the best place to be is that upper right quadrant, the IT-enabled growth, where we got low spending, high sales. That seems to be the best place to be, of course. Of course, by the numbers, most businesses are in the bottom left quadrant, maintenance zone. Average spending, low sales. Yeah, so according to Ackoff's principle, we will want to move up to the top left, but Adam calls that the alignment trap, where he says, well, okay, we've got the highest spending of all those zones, and this is backed, by this study. These are real figures, and the lowest sales. So it's actually probably the worst quadrant to be in. Whereas the well-oiled IT, the bottom right, has the lowest spending and not the highest, but high sales. That's actually a far better place to be if you're going to be in any quadrant other than the yellow zone. And in fact, moving from the green zone to the yellow zone, just moving up from well-oiled IT to IT-enabled growth, is actually the simpler transition, Alan argues. Again, we're just summarizing here. Watch Alan's talk for more details. It's a fascinating dissection of this. And the reason for this, and the reason that software development is different, is because when we're doing things right, we're actually working to enable change. We're both our software infrastructure and the design of our code, it's all about low cost of change, easier to change direction. So getting that right first will actually put us in the best position to move up. And Alan goes further and says that most of the time we don't even know what the right thing is until we start doing it. So you start doing it, and then you have a low cost to change direction will get us to where we need to be. So really interesting analysis of the problem and the intersection of the correctness and applicability spaces. So I'm going to move on because we've got a few of these to get through. I want to now have a look at correctness again and reliability. So when we're talking about correctness, we're mostly here talking about obviously how correct the code is, whether it's bug-free. Whereas reliability is more about covering all paths, particularly error paths, which are often hidden. So the intersection of those two, you can see how that's core to software quality. So this is actually going to be the biggest section of this talk. So a big part of this is what we might call code coverage. So code coverage, there are tools that can measure code coverage, but really what we're talking about is we have tests. So testing is the starting point for this. How well do they actually cover the code? That's what the metric's about. And if you use code coverage tools, they usually break down into either line or statement-based coverage. They're slightly different, but approximately the same thing. It's a subtle difference, but it's worth knowing what your tool actually does. So as I said, this is the domain of particularly unit testing, but especially works well with TDD. In fact, if you're doing TDD, test-driven development, properly, by the book, you should end up with 100% code coverage. So do you even need a tool to measure that? It's debatable. No harm in doing it. But using a code coverage tool can actually give you a false sense of security. If you're doing TDD, as I say, you can get 100% code coverage quite easily. But does that mean that all of your code is actually tested? Well, no, because you've got different paths through the code, different data values that may be exercised at different points. And that's very often where the problems come in. So we really need data coverage as well. And there, as far as I know, there are no automated tools for measuring that. In fact, if you think about it, to a first approximation, it's pretty much impossible for any non-trivial code base. So what can we do here? So if unit testing and TDD are not enough to give us good data coverage, what tools can we use? Here's my recommendations. First of all, something called property-based testing. If you've not seen property-based testing yet, I do encourage you to give it a good look. This is not going to be a talk on it. I'm only mentioning it in passing. But whereas with unit tests, you're usually doing what we call example-based testing, where you're saying for these particular values, I expect this particular result. And if you can think of that ahead of time, even better. Property-based testing says, well, for any value, what properties will hold? And then you can actually use the framework to generate the values for you, usually randomly, and you may pick a few sort of known problematic values, but usually it's just a random selection. And then every time you run the tool, it's going to give you different random values, and you'll progressively cover the entire data space, if you like. So it doesn't give you 100% coverage, but it gets you about as far as I know of being able to get there. So do look into property-based testing if you've not done so already. Closely related to that, slightly different, usually at a high level, very often more sort of end-to-end, is fuzz testing. Very similar property of using random inputs, although a lot of it's more tuned to sort of known problematic cases, particularly looking for things that are going to break your system. I know a bit less about fuzz testing. I just know it in the general sense, so I can't talk too much to the specifics beyond that. But definitely another one to have in your toolkit. And don't forget about manual testing. We want to automate what we can, But what's left are the things, by definition, we can't automate. That sort of mindset of breaking things is really valuable in a manual tester. If you have access to manual testers, do use them and do respect them as well, because they're doing something that we've not been able to do when writing the code. So between these three things, this is the best way that I know of to achieve high data coverage in our code, and therefore better correctness and reliability. Now, there's another part to this. I mentioned that often the parts that we don't cover very well are error paths, often because they could be hidden, particularly if we're using exceptions. But these break down into two types of error path. We've got what I call I/O errors, sometimes called disappointments. So these are things that we need to plan for. They are flows through the code that are completely legitimate, but they're not necessarily what we want. They're when we couldn't do what we actually wanted, we'll do something else instead. We're all disappointed. So anytime that you are, say, using error codes or exceptions or some of the other tools we're going to look at, really, these are I/O errors or disappointments. And then the other side are what we might call logic errors, aka bugs. And this is more the domain of contracts in the general sense. We'll look at that in a bit. And it's really important to distinguish between these two. We'll see why in a bit. Let's just have a look at an example of the first category, the disappointments. Very simple example, the function that's converting a string to an integer. Takes a string view. Going to use a string internally. Not the best implementation, but it serves the purpose. Okay, now if we try to call this function with a string that's not an integer or doesn't encode an integer, what's the result we're going to get? Well, we get a 0. Yeah? And that is perfectly understandable if you know how string works and predictable, but not particularly useful, because we can't distinguish that from an actual return value if we'd actually given it a string that had a 0 in it, that there's no difference. Of course, you could argue that's a problem with string, that the API is not very ergonomic, and that's true. String's not really optimized for that, of course. Our function should be, so we should do better. We can, of course, test the stream, to see whether it is good and take some other action. We might choose to throw an exception, and that would be a reasonable choice. Probably not the best choice for this particular example. Very often you want to use this function to actually test whether the string had an integer, and if so, then do something with it. So we want to have that a little bit more sort of in line, if you like. So one way to achieve that will be to use a std optional. I'm guessing most people are pretty familiar with how std optional works now, so I'm not going to go into it in too much detail, but just have a look at the usage. We might write code like this because we can take advantage of the fact that an optional models pointer semantics, in that we can test them for explicit Boolean conversions, and we can dereference them again like a pointer. This is much better. Now we can actually distinguish between the error case and the non-error case. Good. Still a bit of a problem though, because while we can test before we dereference, we're not forced to by the API. We could just dereference what we're returning. Maybe we hadn't thought it through, and we end up with, in this case, undefined behavior, which is probably not what we wanted. So a little bit of a weakness in this API. Now in C++23, we're going to get the so-called monadic operations, map, bind, and or else. If talk of monads scares you, don't worry, pretty straightforward. In fact, this code does pretty much what the previous code did. So we do map for the case where we have a value in the optional, and or else where we don't. There's also bind, where we can actually bind it to another thing that also returns an optional. Now, the difference here is that map case, we're getting the already dereferenced value. We don't have to manually dereference it. So therefore, we can't actually get it wrong. Of course, we can still dereference the optional if we hold on to it somewhere. So that's the trouble with C++. We can never fully remove all the problematic legacy code, but this gives us a safer way to do things, and actually scales up quite nicely once you get used to it. So nice addition to C++ 23. There's other ways, of course, to deal with disappointments. We mentioned exceptions in passing. See my other talks for why you might not want to use exceptions. Good old error codes, at least if you use no discard, it's still a good option, if you pardon the pun. Optional, of course, we just mentioned. If you are going to use error codes, though, do consider stood error code as a way of interacting with it. Very underused. We've had it since C++ 11. It's got lots of nice features. Even boost outcome. I'm not going to go into that in depth now, but it gives you sort of a halfway house between error codes and exceptions. And coming in the future, stood expected is also, I believe, just been adopted into C++ 23. And if you're not familiar with stood expected, it works much the same as stood optional, but in the error case or the empty case, you get a place to put another type that can indicate what the error was about. So again, giving you back some of the things that we lost from exceptions. And although it's not been much activity recently on P0709, that's the Herb Sutter's proposal for what we might call static exceptions, been the subject of a couple of my talks. I believe that's still on the table, even if not as in the paper. I think something's going to come out of that, so it's one to watch as well in the future. But at least stood expected is on its way. So we have quite a rich set of ways to deal with disappointments. So do make sure you're familiar with all of them and actually use them. The other side to the branch, is those logic errors. I mentioned contracts. So probably know contracts, the language feature, we're going into C++ 20, got pulled at the last minute. Unfortunately, it's looking like they're going to miss C++ 23 as well. There may still be time, but I think it's unlikely at this point. We will get them in a language at some point. But in the meantime, we can still use things like assert statements. There are also third-party libraries that will do it. But what are we really talking about here? Let's have a look at another example. So let's consider another function now. This one to convert a month number into a string. So we passed in an integer, returns a string. So almost the opposite of our previous example. Now looking at that integer, we can note that an integer has a range. Pretty big range, minus 2 billion to plus 2 billion. But it also has a domain. And that's the range again, if you like, of valid values for this function. So this function is only defined for values between 1 and 12. And anything else is an error of some type, yet to be determined. Whenever we have a difference between the range and the domain, obviously we have to deal with that somehow. One way we could do that is we test up front and maybe throw an exception. So similar to our previous example. Trouble with that is you might want to call this when you have an integer that you know is a valid month, either because it's a literal or because it's been pre-validated somewhere. You don't want to have to pay the cost of that checking if you know that it's going to be valid. It's a C++. We don't want to pay for what we don't use. We may have, let's say, pre-validated something and we keep passing it to functions that take month numbers. We don't want to check it every single time. So in that case, we might use, let's say today, we can use an assert statement. Hopefully in the future, it will be a precondition, but amounts to the same thing. It's a check that we can disable in an optimized build. We're saying this is only a check for debugging purposes, development purposes. In production, we expect it to always be passed a valid value. And if it's not, it's going to be undefined behavior again. But we're just trying to protect ourselves from it. Did you notice, by the way, the bubbles at the top? We added that efficiency bubble for this section. That's because now we're looking at areas that we can remove unnecessary checks. And undefined behavior often comes hand in hand with attempts to improve performance. Okay, obviously there's some problems with this, though, at least so far. It's fine to say this month number needs to be pre-validated before it's called. In practice, that can be problematic, especially if the logic of what is a valid value is encoded in the implementation of the function. Now, in this case, it might be simple enough, but I mean, how do you know that we're not looking at integers between 0 and 11, for example? And it's still got to be documented somewhere. Lots of opportunities for this to go wrong. And remember that the danger is undefined behavior. So we might want to factor out that check to a separate function. In this case, is valid month. So now the month for string function can assert on that. If you want to pre-validate before calling it, you can use the same function. So it should be fine. If that implementation ever changes, you're still good. But now we're back in the same situation we had with optional earlier, where we can pre-validate, but we're not required to, which was sort of what we wanted. So how can we get around this? Well, we could add a wrapper function. I call this one month for string checked, that does the check and then calls the I haven't written it here, but calls the month for string function. And if it wasn't valid, we'll take some other action. I'm throwing an exception here. We could use error codes or optional, expected, whatever. That's up to us. So now we've got two functions. We can call month for string if we know it's pre-validated, or month for string checked if we want that to do the checking. You might prefer to do that the other way around. Month for string unchecked, so the more wordy function name for the thing that has the undefined behavior, sort of like a here be dragons annotation, if you like. And then supposedly month for string is safer because it always does the check. But there's two schools of thought on this. And some people are insistent that the default one, if you like, the one without the extra word, should be the one that has the undefined behavior, because calling it without checking should always be an error. And you don't want to hide that error with maybe some sloppy exception handling, for example. I usually lean towards this form with the unchecked suffix, and it served me well over the years. I am sympathetic to the other side of the argument as well. But I think there's more that we can do to stack this more in my favor. So remember, this is all because of the difference between the range and the domain in this case. Now, if we had a language like Ada, then we could have bounded integers built in. Here's an example from Wikipedia with Ada actually doing a date type, and you can see there we've got month type actually defined as values within the range 1 to 12. So it's right there in the language. That makes things, you don't have to, if you've got a month, you know that it's valid at that point. Now, there are bounded integer libraries for C++. We should probably consider using them if that sort of thing is important to us. Of course, you can also roll your own custom type. This is sort of an example of strong types, but it's more than that because it's actually validating the domain as well. So here we've got a month wrapper, just holds the integer, but it does the check in the constructor. In this case, it's throwing an exception. This is simplified for slide where you might want to have something slightly more sophisticated and capable if you're doing this for real. But now we can write our month as string, just taking a month. We don't have to check because we know it's guaranteed by the type system that this is pre-checked. Now, say it's guaranteed, obviously bugs can still creep in. You can still check again in an assertion, but you can assume that this has been pre-checked. And that means no matter how many functions that take month numbers you pass this to, we only have to do the check once. And we can push that check as close to our boundary, as close to the point where we get untrusted input as possible. And I think that's what shifts it for me towards having the default be the one that's checked at runtime. So our constructor for month here always checks and throws an exception. But of course, we may still want to construct months in an environment where we have a pre-validated month number. We still want that unchecked version. Of course, we can't have differently spelled constructors, at least not yet. But there are techniques for getting around that. I usually use a tag type, so just an empty type that's only purpose is for the purpose of overloading. So now we can have another constructor that just does the assert, and now we can construct a month from an integer that will throw if it's invalid, or a month from an integer and an unchecked tag that asserts. I think that's the right way around. This is part of what's often called falling into the pit of success. You make it easy to do the safer thing, but the more performant things are still possible. So for me, this is a sweet spot. There's a little bit more machinery involved. It's not going to be applicable everywhere, at least not until we get better language support. But these are things I'd definitely recommend considering doing if you're not already doing at least in key parts of your code, because they really can make things closer to that sweet spot between reliability, correctness, and efficiency. Getting all three is usually elusive, but these are techniques that can get us closer to it. So, coming back to our list, the next pairing I want to look at is between reasonability and evolvability. Now, I mentioned that these were very closely related anyway, so maybe not such a surprising pairing. But the way we get there, I find, is usually by keeping our code simple. We'll have a look at exactly what that means in a moment. But for me, that usually implies using functional programming techniques, particularly focus on immutability and correct by construction techniques, which is sort of what we just looked at with that month example. Once you have a month, you don't have to check it again because you know it's valid. Now, I've done that talk on simplicity, and one of the slides from there that I use the most often is this one, which I actually stole at least the illustrations from a talk by Rich Hickey, Simple Made Easy, where he traced back the origins of the English words simple and complex to the Latin words simplex and complex. So a complex in Latin means many folds or braids, or a thing with many folds or braids, whereas a simplex is something with only one fold or braid, or at most one. So it's not so much the number of things as the number of crossing overs, as the illustrations bear out. The consequence of that, if you look at the illustrations, following one of those strands on the simple side, from top to bottom, or bottom to top, is trivial. You can do it at a single glance. On the complex side, if you follow one of the threads from the bottom to the top, you've got to carefully follow all the way around to see where it ends up. And we're only talking about a few things crossing over there. So this is really what complexity is about. Things that are interacting or crossing over, particularly where they don't need to be, they make it very much harder to reason about. In fact, it very quickly gets impossible. And we just give up reasoning about it, and we just have to use heuristics or guesses. What causes complexity in code? Well, this is the list that I've come up with. Maybe you can think of others. If you do, let me know. I'll add it to the list. But this is a pretty good list. Most of them should be fairly self-evident. I'm not going to go through them one by one. I just want to pick out two that I think is worth mentioning. One is leaky abstractions. Go into this much more in my simplicity talk, but abstractions are one of our main tools in the fight against complexity. But the tragedy is that they very often make things more complex. And the reason is most abstractions, in fact, really all abstractions, are leaky, which means that as well as the abstraction itself, you're dealing with the thing that it's abstracting a lot of the time, leaking through. And that means you've now complicated or complexing, as Rich Hickey likes to say, the abstraction with the thing it's abstracting. It's made it more complex. So there can really be a double-edged sword if you don't use them the right way. So I talk about that much more in my other talk. Do watch that if you're interested. The other thing I wanted to point out from here is mutability. Because, again, using Rich Hickey's word, complexing, it complex the value of something with the passage of time. Value and time. So to reason about the value of something, you have to consider where it is on the timeline. And like following that thread up, that means you have to consider everything that it passes through. Something is immutable, then You only have one place that you need to reason about its value. So it's one of the biggest areas of complexity, unnecessary complexity in code that I see, particularly with a language like C++, where mutability is the default. And we have to work a little bit extra to achieve immutability. I think it's worth it. So it turns out that lowering complexity not only makes things easier to reason about, but also easier to test and easier to change. And these three things generally come together because, particularly if you are doing TDD, I'll bring that up again, then if something is hard to reason about or hard to change, your tests will tell you because the test will be hard to write. So when you hear TDD people talking about listening to the tests, that's what they're talking about. What is the test telling you about the complexity of the code? And you get the earliest opportunity to fix that before it becomes too hard to do so. So please use techniques like TDD to help you to understand where your code is too complex. Make it easier to reason about and easier to change. So my magic formula for lowering complexity is the combination of TDD and certain functional programming techniques. You don't have to embrace the whole thing, but particularly that focus on immutability and other things which increase the simplicity of the code. Okay, starting to run a little bit short on time. Got a couple more of these to get through. Reasonability and efficiency is the next pairing. Now, we already sort of looked at this intersection earlier as well, but this one I want to revisit. Why do we even need to think about this? Why is it usually a trade-off? And it's usually just because of this. To make things easier to reason about, we generally want to write high-level code, maybe in a high-level language. But we're addressing the low-level machine, and working at the level of the low-level machine is usually where we're going to get the most efficiency. So some time ago, we invented what we call systems languages to try to sort of sit in the middle, a bit closer to the low-level machine. C++ was an attempt to sort of move it up a bit while still giving you access. But the trouble is that those low-level machines that systems languages were built around or designed around, particularly C and the C-based languages, it's basically the PDP-11. That was the mainstream machine at the time that C at least was being formulated. And so there's a lot of assumptions about what low-level code is that's based on the model of the PDP-11. But we've moved on a lot since then, particularly in how our processors are optimize things. So trying to work at that level now, if you don't know what you're doing, or even if you do, very often attempts to optimize are going to backfire. So we obviously have to be very careful. But we're talking here about that intersection between reasonability and efficiency. Rather than seeing it as a trade-off, often you can actually get them to work together, because code that's easy for you to reason about is often easy for the compiler to work and reason about as well. And very often where there is a mismatch, it's because compilers are actually trying to work with the ways that programmers have tried to optimize things. So that they'll work better that way. But we're actually moving more and more to a world where compilers are understanding higher level abstractions in a way that they can reason about and actually produce more optimal code. Just to look at a really simple example where sometimes things can be surprising. So this is an example from my functional programming talk. So some simple code where you want to set some color enum, but in order to do so, you need to call some other function that will tell you which way to go. Pretty straightforward stuff. Here's how you might write it. Even in just these few lines of supposedly simple code, we've got a number of problems. So because we're having to use an if statement as a statement, not an expression, we have to assign to our color, which is another statement. And that means we have to pre-declare it with an uninitialized value, or perhaps even worse, an initialized value, but to a value we didn't actually want. And then test the condition and as a side effect, perform that assignment. And now our color also can't be immutable, can't be const, which means to reason about it, we have to look through all of the rest of the code that it might exist in to see if anything changes it. So quite a few problems for just a small snippet of code. Now, of course, in C++, we can address that by using the ternary operator. So might do something like this, achieves the same goal, but that we can make it const. There's no side effects. It's all through initialization rather than assignment. And as a side effect, if you pardon the pun, we get type inference in there as well, because now it's all initialized. Great. All right, we can do that, but it breaks down a bit if you do something more complex, like a switch statement. Now we've got more than two branches. We don't have the equivalent of the ternary operator for that. Functional languages, which is why I bring that up, tend to have constructs like this that are expressions rather than statements, and therefore you would be able to do this. But we can fake it in C++ using the technique of the immediately invoked lambda expression. So we wrap our switch statement, in this case, in a lambda, immediately invoke it at the end. You see the parentheses at the end there, that's important. It's immediately invoked, and although we're actually using another statement in there, the return statement, to get out of the switch, that's what's effectively making it like a fake expression, because we'll use that value to immediately initialize our enum, and we get all those benefits back. Made it const, we can make it auto. There's no visible side effects. Now, why am I talking about efficiency here? A lot of people, when they first see this, will think, oh, now I've got the overhead of the function call, the lambda. By now, we're probably familiar with the fact that that's going to get optimized out. So at worst, it should actually be about the same as the code we wrote before with the side effects. But if instead of an enum, we had some more expensive type, something like this maybe, that is copying values into a vector, then doing something similar may actually be more efficient this way, because we haven't had to expensively construct the object in one state and then immediately assign it to another state, because we've done it all in a single expression effectively. We've both raised the level of abstraction and reasonability and efficiency at the same time. Obviously, that doesn't always happen. In fact, very often you'll still have to make your code harder to reason about to make it more efficient. But take the wins where you can. And of course, making code that's easy to reason about first and then optimizing it is usually the much easier way. If you are going down that path, there's another approach you can take as well. Again, not all the time. But this comes back to testing. Testing plays a role here again, and specifically property-based testing. So I mentioned that more at the start. This is actually a slight abuse of property-based testing because we're not really testing properties. But take the example of some sort of algorithm that you've written, and there's a really heavily optimized version of this algorithm that's really hard to reason about and verify by inspection that it's correct, but it's much more performant. But there's also a slow, easy to reason about implementation, but it's just too slow. What you can do is you can test one in terms of the other using property-based testing. And here I'm using an example from Catch, which has partial support for property-based testing. So in this case, we can just call the first one and the second version with the same values, which are randomly generated, and just verify they produce these same results. Now, it's usually not quite as clean as that in real-world code. They may not give you exactly the same results. There may be some tolerances you need to build in there, but you can usually still follow this pattern pretty closely. I've done it before. It works quite effectively. Again, it's not a technique for every occasion, but do consider it. It can actually help you to have both the reasonable, easy to reason about version of the code and the efficient version, and know that they're both correct. So we are running out of time, so just getting into the final section now. There are other intersections, but we've looked at quite a few. And in fact, you can see there's some sort of redundant pairings there. If we filter those out and if we drop that link between reasonability and reliability, we actually get quite a nice stack there. It's a good place to sum up. Along the way, as we visited all these intersections, there are three common themes that reoccurred. Testing, both property-based testing and TDD, using the type system to our advantage, and attention to error handling, which were coincidentally very closely related to those categories of talks that I started out with. There's something else that relates to all of these that I haven't mentioned yet, and that's use of static and dynamic analysis tools. We have plenty of these days. That will touch just about every step in this chain. And one of the main reasons that I've now moved to Sonar Source, because we do static analysis tools. So talk a bit about that afterwards, if you like. But do make sure you're aware of what tools are available and use them, because getting all of this right is too much for humans to do on their own. Using tools is the only way we're really going to get all the way there. So finally, I want to quote from an article by Michael Feathers. Now, don't get put off by the title, The Flawed Theory Behind Unit Testing. He supports unit testing. It's a very interesting article, though. But I want to look at this quote. He says, in the software industry, we've been chasing quality for years. So that's why it's on theme. The interesting thing is there's a number of things that work. Design by contract works. We talked about contracts. Test-driven development works. We talked about TDD. So do clean room. We didn't talk about that. Code inspections and the use of high-level languages. We did talk about that. Wrong way. I'm going to go the other way. There we go. Next paragraph. All of these techniques have been shown to increase quality. And if we look closely, we can see why. All of them force us to reflect on our code. That's the magic, and it's why unit testing works also. When you write unit tests, TDD style, or after your development, you scrutinize, you think, and often you prevent problems without even encountering a test failure. So Michael Feathers' main takeaway from this, there's a whole story here that you should read, but this conclusion is that it's actually just scrutinizing the code, thinking and reflecting on the code, that is the main technique we have for improving code quality. So with that, I want to take us full circle back to our title and mention Zen. So the word Zen originally meant meditation. And Wikipedia, in the section meditation, says that it's focusing the mind on a particular object, thought, or activity to train attention and awareness and achieve a mentally clear and stable state. Compare that to what Michael Feathers said about reflecting on the code, giving it scrutiny. Perhaps Zen is actually core to code lifecycle maintenance after all. So that is the end of my talk. There's a link there to a page on my website where I have all of the references for all of the other talks and blog posts and everything else that I've mentioned. In fact, I'm going to place that into the chat as well for those watching live, just to save you having to type that in. But thank you very much for watching. And do we have any time for questions?
Phil, thank you very much. It was very cool. And before we will go to the Zoom, I have a small question. Okay. Have we got enough tools, or maybe can we make a full-featured property-based testing without I forget this word, reflection, without reflection in C++? What do you think about it? Can we do?
I don't think we need reflection. that there is a full property-based testing framework for C++, called CPP check. I always forget the name of it. Not sure, it may be linked in my references actually. As I said during the talk, Catch 2 has partial support for property-based testing. You have the generators. The bit that it doesn't do is what's called shrinking, where once it's found a failure, it'll then try to give you the simplest version of that failure, which can really be a big help in a lot of cases. So it doesn't do that part, whereas this other tool does. Beyond that, I don't think there's really any need for reflection that I know of. So yeah, you can definitely do it.
Okay, it's cool. And we have time for one more question. What do you think about efficient code and testable code? Are they in concurrency? Are they in conflict or not?
The correct answer is, of course, it depends.
Okay, but in your experience,
so that's what I tried to bring out in the section on that. That yeah, they may be in conflict, but sometimes they actually go hand in hand, because if you make your code easy to reason about to a human, it can be easy to reason about for a compiler. So it has more scope for doing the right thing. The purpose of that example I gave with the immediately invoked lambda expression is because it now knows that nothing happens between the initialization and actually getting the value that you wanted. Then it doesn't have to generate any unnecessary code for that. It's just one example. But yeah, obviously, there's still going to be cases where they're in conflict. But even then, starting from something that's simple but works and optimizing it towards something that's more performant is usually going to give you better results than starting straight for the more performant one. There's still going to be cases where even that can mislead you, but I think as a general principle, that's still sound. And then there's also the technique that I presented on using a property-based testing framework to verify your optimized version against the unoptimized version, just to make sure that it's still doing the same job. So yeah, if you use those approaches, you can reduce the conflict. You'll never be able to eliminate it.
Okay, thank you. In my experience, testable code, it's not the same and efficient. It's my pure experience. I'm sorry.
So what you need to do is come to my TDD course, and I'll give you more information.
Thank you. I will do it. Okay, and I think that we can go to the Zoom. Where is the link? Okay, I got it. And then I think that we can discuss the topic, how we can ensure that our tests are correct, how we can trust them. Mm-hmm. Let's discuss it in the Zoom, okay?
I have thoughts, okay? We'll see you all there.
Okay.